difficulties of getting here from Britain this morning. Okay, so what I'm going to talk about is joint work with Zanya Gadanejad and Catherine Tent. What I'm going to do is describe some fairly general machinery for studying the normal subgroup structure of automorphism groups of countable structures. The machinery will be particularly applicable when the structure has some sort of notion of independence or some sort of free amalgamation associated to it. Okay? And what we're going to do is apply this to certain structures obtained using the Hrushovski amalgamation method. Okay? So at various points, I'll tell you what the machinery is, and I'll remind you of some of the things about the Hrushovski constructions. But let's begin with some very classical results. The first result, Schreier and Ulam. Suppose you've got a countably infinite set X. If you've got a permutation G, which moves infinitely many elements of X, then every element of the symmetric group is a product of a certain number of conjugates of G. Some of you probably know what the minimum value of that number of conjugates could be taken to be. I'm not sure I can remember. But the point is that if you've got a normal subgroup of the symmetric group which contains that element G, it has to be the whole of the symmetric group. Another way of saying this is that if you take the symmetric group modulo the finitary permutations, so the ones which only move a finite number of elements, then you get a simple group. So that's a classical result. There's a corresponding result for the general linear group, so the invertible transformations on a vector space V. Let's take V to be a vector space of countably infinite dimension over a field K. You can actually take a division ring here if you want. So FGLV will denote the elements of the general linear group, the invertible linear transformations, which have a fixed point space of finite codimension. And then the result here is that the general linear group modulo scalar multiples of these finitary transformations is a simple group. Yeah, so if you take something outside that, then every invertible linear transformation of V can be written as a product of conjugates of it. Okay, another classical result, Graham-Higman, looking at the normal subgroups of the order-preserving permutations of the rationals. The non-trivial proper normal subgroups are the left-bounded automorphisms, so those that fix all rationals below a certain rational A there. The right-bounded automorphisms, and you can see there's a typo there, and the intersection of these, so the bounded automorphisms, and then you've just got the trivial group and the whole group giving you the normal subgroups. So this is a slide of classical results. So probably 1985. It's by now a classical result of John Truss. Well, I remember being in Oxford when this was proved, and people were surprised by this, I think. So you take the countable random graph, its automorphism group is simple. Very nice result of John, which sort of started off a whole lot of realization that you could actually investigate automorphism groups in general, perhaps, in the way that people have been looking at finite groups. I don't know. Okay, so, but there is a warning here. It's tempting, perhaps, to believe that things are too nice. So you might believe that automorphism groups of nice countable structures shouldn't have any sort of non-obvious normal subgroups. But there's this example of Manfred Dross, Charles Holland, and Dougal McPherson, something called take a countable homogeneous semilinear order. So that's some sort of partially ordered set. Well, it is a partially ordered set. Below every point, you have just a chain, and any two elements have a lower bound. And the ones in question here, you have are two homogeneous, so any pair of elements, one less than another, can be taken to any other pair of elements, one less than the other. And you have transitivity on pairs of incomparable elements, then the automorphism group of that has rather too many normal subgroups to actually describe, say, in L omega 1 omega or anything. Yeah. So, they are, in some sense, though, all bounded. Yeah? So maybe there's something going on. Okay, so those are some sort of examples. Most of what I'm talking about consists of general results which somehow develop on from this theorem of Daniel Laskar in 1992. So it's phrased in sort of model theoretic terminology. If you don't know what the model theory actually means, then it doesn't actually matter. The impressive part about this result is it's a general result. So let's just read it anyway. So suppose M is a countable saturated structure with a zero definable strongly minimal set. Could actually be a strongly minimal set. That's still interesting. And we'll suppose that M is the algebraic closure of that strongly minimal set. Suppose that you've got an automorphism G which is unbounded in the sense that for every n, there's some finite subset of the strongly minimal subset which gets moved to something of dimension at least n over itself. Then G is generated by the conjugates of G. Okay, so at least you can see what the conclusion is, even if you don't know what a strongly minimal set is. So strongly minimal sets, they're first-order structures which you can't definably split into two infinite pieces. So examples are things like the whole is just a pure set or a vector space over a finite field, over a field in the appropriate language, or an algebraically closed field. So they're important structures. And here's a general result about automorphism groups of such things. Okay, so a strongly minimal set automatically comes with a notion of dimension. There's a notion of closure associated with them. In this case, it's algebraic closure. And okay, so these features, dimension and some sort of closure, will reappear in the more general setting later on. Okay, so this implies the results for the symmetric group and the general linear group. One very nice aspect of it is that it makes good use of the topology on the automorphism group and uses Polish group arguments. It has been used to prove sort of new group theoretic results. Tim Gardner in 1995 used this to prove the analog of Rosenberg's result, the one about the general linear groups, for classical groups over finite fields. So these are the orthogonal symplectic unitary groups. So again, the result there is that modulo scalar multiples of the finite tree transformations, the automorphism group is simple. More recently, it was used by Zanier and Katrin to prove the simplicity of the automorphism groups of certain generalized polygons which Katrin had constructed several years previously, and so obtain new examples of simple groups with a Bn pair. So simple groups with a Bn pair which don't come from algebraic groups. Yeah. Okay, so let me sort of talk about things which perhaps don't mention so much model theoretic terminology. A couple of years ago, Dugald and Katrin, I think based on, or from looking at Laskar's result, and certainly using some of the same ideas as Laskar used, proved the following. So suppose you've got a countable, transitive, homogeneous relational structure whose age has free amalgamation. And so free amalgamation, remember, means you've got two structures which you want to amalgamate over a common substructure. You just take the disjoint union of those over the common substructure, and you don't put any extra relations between the bits that lie outside the two given structures. Okay, so that's free amalgamation. So suppose your homogeneous, the age of your homogeneous structure has free amalgamation. Suppose that your structure really is something other than just a pure set, so the automorphism group isn't just the symmetric group on the set. Then the automorphism group is simple. And Julien Melleret pointed out that you actually get a bound from the Polish group argument here if you take a non-identity element of the automorphism group, then every element of the automorphism group is a product of 32 conjugates of G or its inverse. Okay. So of course, in particular, this implies Truss's result from 1985 because finite graphs, what you see in the age of the random graph, they have free amalgamation. You'd be crazy not to prove the amalgamation property for finite graphs by free amalgamation. Yeah. Okay, it also implies some, I think, unpublished results of Matty from around about 1988. Yeah. Okay, right. Okay, so Katerine and Martin Ziegler generalized this a bit further to the case where M has what they call a stationary independence relation. That's that strange symbol there. And applied this sort of more general setting to prove the following about the Urisohn rational metric space. So suppose U is that. If you take an automorphism of the Urisohn rational metric space which is not bounded, which means that for any n you can find a point which gets moved a distance bigger than n by this automorphism. Okay, so if G is not bounded, then every automorphism of U can be written as a product of 8 conjugates of G. Okay, so that's using this sort of extension of the technology. So I'll tell you about stationary independence relations very shortly. Okay, like now, in fact. Okay, so this is an axiomatic framework. So it's going to be a bit, well, unpleasant, I think. But just try and get sort of the idea rather than worrying too much about the details. It's, for anyone who knows a bit of model theory, you can see that what's going on here is modeled very closely on what the stability theorists do, the notion of non-forking or whatever. And some model theorists are very adept at manipulating this sort of notion. But we're going to just treat it axiomatically. I'm not assuming anything about stability here. Okay, well, let's get on with it. So let's take M, a countable first-order structure. Its automorphism group will be called G. On G, we will have a closure operation, CL. It should be invariant under the group, and it should be finitary in the sense that the closure of a set should just be the union of the closures of its finite subsets. So it's all determined by what happens, closures of finite sets. Okay? I also want it to be not too strange, so it should have something to do with the automorphism group apart from being invariant. So that's the fourth bullet point there. If X is a finite subset of M and A is fixed by by all automorphisms which fix every element of X, then A should be in the closure. So if you know what this means, it's saying that essentially the closure should be at least as big as the definable closure. Okay, so I'm using this notation G subscript X there. G subscript X is the subgroup of the automorphism group which fixes all elements in X. Okay, so we're going to have this closure operation around, and I want script X there to denote the closures of the finite subsets of my structure. Yeah. And occasionally, we'll need this script f, which will consist of all maps which extend to automorphisms, all maps with domain are closed, the closure, something in X, yeah? So closure of a finite subset. Yeah? So those are what I mean by partial automorphisms. Yeah? So the domain has to be closed. Okay, so you could take the closure to be algebraic closure in M. So, for example, if M was an omega categorical structure, then the algebraic closure of X is the union of the finite GX orbits. That's a decent closure operation. This is even interesting if if the closure of X is equal to X for every X. I mean, the framework is still going to be interesting in that case. So if you're uncomfortable with this closure operation, just imagine that it doesn't really do very much. So, for example, if M was the Frese limit of a free amalgamation class, then the algebraic closure would be trivial in this sense. Okay, so the next slide contains the axiomatics for this notion of independence. And what it is, it's going to be a relation between subsets of M, and it's going to be written like this. So this is pronounced A is independent from C over B. If you want something to hold in your mind, whilst we're doing this, you could imagine that it just means B contains the intersection of A and C, or something like that. Or you could imagine the vector space example, and it means A is linearly independent from C over B, or something like that. Yeah? Okay, so here's the axiomatics. All right, there'll be a test at the end. I probably need some sort of siren to go past. It's a police car or fire engine or something. But, okay, so we're going to say that this symbol, this relation is a stationary independence relation compatible with the given closure if for all A, B, C, and D, which are closures of finite sets and finite tuples A and B, well, the first one says this is really about closed sets. So, for example, if A is independent from C over B, then that happens if A is independent from C over the closure of B. Yeah? This is a perfectly reasonable thing. And you can see various other things. Basically, I can just apply closure to any of the symbols decorating this anchor sign, and it should not affect the truth or otherwise. Okay, the second is perfectly reasonable. I want it to be invariant under the action of the group. Yeah? So if A is independent from C over B, then GA is independent from GC over GB. Skip 3 and 4 for now, and look at 5. This is also seemingly quite reasonable. If A is independent from C over B, then C should be independent from A over B. Yeah, that's the sort of thing you might expect from independence. And then there are things 6 and 7 which say that the group can move things around so that they're independent, or if they're independent, then they look very much the same. So 6 says, let's just read it. If I'm given A, B, and C, then there's an automorphism of G fixing B. Sorry, there's an automorphism G fixing B, which moves A to something which is independent from C over B. So if this were algebraic closure, this is we just meant by this intersection, we might be saying something like, if A, B, and C are algebraically closed, then I can move A so that its intersection with C is contained in B, yeah? Using an automorphism which fixes B. So then it becomes something like Neumann's sometimes called. Okay, so, and then stationarity is the sort of key property here. This is the hard one that, to obtain. I was wondering whether to attempt to use the board. I'll be able to see it, but probably no one else will. So I don't know. Let's just say it. So suppose we're given A1, A2, B, and C. They're all closures of finite sets. B is contained in A1 and A2, and A1 and A2, each of them is independent from C over B. Yeah? Now, imagine you've got a partial automorphism from A1 to A2, which fixes everything in B. Then you can extend that to an automorphism of the whole structure, which fixes everything in C. That's what stationarity says. Yeah? So if A1 and A2 look the same over B, then they look the same over C. Okay? As long as A1 and A2 are independent from C over B. Okay, so that's a strong property. Going back to monotonicity and transitivity, they're sort of opposite sides of the same thing. So it's easier if you imagine, for example, for transitivity, it's easier if you imagine that that B is contained in C and C is contained in D. If we imagine that and then read it, if A is independent from B over C and A is independent from C over D, then A is independent from D over B. Yeah? If you had those containments, that's how it would read. Okay? And then monotonicity is sort of the converse of that. Okay, so we've got this axiomatic framework. And if I've done it right, it sort of implies some other things that you really ought to that really ought to be true. So for all A in M and finite X, A should be independent from the closure of X over X, and things like that. That comes from compatibility. And A should be independent from itself over X. Well, that should really only happen if A is in the closure of X. Yeah? So you get sort of things like that. Yeah? So this notion appears in the paper of Tent and Ziegler, where algebraic closure is trivial. And the closure operation is then taken also to be the trivial closure operation. So you might imagine, trying to find an example of such a thing. You might write down, well, this is the one I mentioned a couple of slides ago. Think that A is independent from C over B to mean A intersect B is contained in B. Then that will satisfy 1 up to 6, but not necessarily the stationarity there. So a better example is given by the free amalgamation example. So suppose M is the Frese limit of a free amalgamation class of relational structures. So algebraic closure will be trivial in that case. And let's take our closure operation here to be trivial. So we will define A independent from C over B to mean, well, A intersects C contained in B, and A together with B and C together with B should be freely amalgamated over B. And this gives you a stationary independence relation. Yeah? The difficult part is that stationarity in general, but you can see what it's saying is just that, well, if you have two free amalgams, then they're isomorphic. Yeah? Two free amalgams of bits that look the same, then they're isomorphic. Okay, so the free amalgamation example is a special case of this. And also the vector space example is a special case of this because you can take your closure to be linear closure, as you might expect, and you can take independence to mean, well, linear independence, or because we're in a vector space, we can say this more neatly. We can say the closure of A together with B intersect the closure of C together with B is just the closure of B. And this gives a stationary independence relation. Okay, so we have got some meaningful examples, even if they're just the same as the ones we had before thus far. Okay, so before I can tell you what the theorem is, I want to talk about the notion of an automorphism, well, moving almost maximally. So sort of not being bounded is the idea here. Okay, so we'll say that G, an automorphism of M, moves almost maximally if for all capital B, so remember X there is closures of finite sets, for all B in X and points A in M, there's something A prime in the GB orbit of A such that A prime is independent from GA prime over B. Yeah. So G moves this copy of A over B to something independent from it over B. Okay, so again, this terminology comes from the 10th Ziegler paper. Okay, so let's, for example, take the vector space example. What happens if a linear transformation here doesn't move almost maximally? Well, that means for some finite dimensional subspace B, it's the same B as up there, and for all vectors, you're going to have that G of the vector is in the linear span of the vector together with B. And so you can see that that means that G is going to act as a scalar on the quotient space. So if you mess around with this a little bit, you can see that G must be a scalar multiple of a finite tree transformation. Yeah? So in this case, not moving almost maximally corresponds to, well, being a scalar multiple of a finite tree transformation. Okay, what happens in the free amalgamation example? Well, roughly speaking, what happens is this. Suppose that, that the automorphism group is transitive on the structure and it's not the whole symmetric group. Take a non-trivial automorphism, and then you show that one shows that it moves infinitely many points in each GB orbit for each finite B. And then using a back and forth argument, you can show that there's some other automorphism H such that the commutator GH moves almost maximally. Yeah? So this, you can't a priori guarantee that G moves almost maximally, but by taking a commutator in this way, you can guarantee that that commutator moves almost maximally. Note that the commutator here is a conjugate of G times G inverse. Yeah. Okay, so so then here is the theorem. So let's suppose we've got a countable structure with one of these stationary independence relations, which is compatible with some closure operation on the structure. And, well, clearly we're going to have some normal subgroup here, things that fix everything in the closure of the empty set. So let's assume that the whole automorphism group fixes the closure of the empty set. So if G moves almost maximally, the result is that every element of the group is a product of 16 conjugates of G. Okay. So in the case where the closure operation is trivial, this is proved in the paper of Tent and Ziegler. And they also point out that it implies that result of McPherson and Tent for the free amalgamation case by the argument that I just gave you. Remember, that was the free amalgamation gives you this stationary independence relation. From what was said at the bottom here, if you take a non-trivial automorphism, then some conjugate of it, sorry, some commutator of it moves almost maximally. So that's using g to the minus 1 times the conjugate of g. Then you want 16 conjugates of that, so that gets you your 32 things, which are products of conjugates of g or g to the minus 1, and that was the result of McPherson intent. Okay, we're going to play this game of how many conjugates do you need? Just to keep you awake. I'm not going to prove anything, but I'm going to do these silly little calculations. Okay. All right. Well, the proof really uses some things from Laskar's paper. The proof in the general case is really the same as the proof in the paper of Tent and Ziegler, just with this closure operation thrown in as well. And it also needs, in the case where this closure operation is not necessarily one which takes a finite set to a finite set. It needs, in that case, a trick from Laskar's paper. So we use a topology on G which has a base of open neighborhoods of this form. You take all automorphisms which extend a given partial function as a basic open set, and you take all of these. That gives you all your basic open sets. If the closure of a finite set is always finite, this is the usual topology of pointwise convergence. But in one of the examples I'm going to give you, and in the examples in general in Laskar's paper, you don't have that condition. Closure of a finite set can be infinite, and so it gives you a different topology. It's not a Polish group topology because it's not separable. It's complete metrizable, but it's not separable. But a trick in Laskar's paper allows you to work in separable closed subgroups. If you put that together with essentially the proof in the Tent-Ziegler paper, then you get this generalization. Okay. So, I could say, are there any questions? Any questions? Okay. Right. So this, I mean, if you've never seen this sort of anchor symbol used before, or then it might be a bit mysterious. Let me try and give you something which seems a bit more reasonable, and this is obtaining these independence relations from dimension functions. Okay, so M is going to be a countable structure. G is going to be its automorphism group. I'm going to say that an integer value function D defined on finite subsets or on tuples from M is a dimension function. If for all finite A and B, it satisfies these two properties. So the first one is that it's invariant under the group, which seems reasonable. So dimension of G of A is the same as the dimension of A. The second one says three things. First thing it says is that the dimension is greater or equal to 0 for every set A. It also says, looking at the second inequality there, that the dimension function is non-decreasing, so the dimension of A together with B is at least as big as the dimension of A. And then the third thing is sometimes called submodularity. The dimension of A together with B is at most the dimension of A plus the dimension of B minus the dimension of the intersection. Okay, so this is a reasonable thing to expect of a dimension function. Okay, and then in the second bullet point there, we can just relativize this. The dimension of A over B is the dimension of A together with B minus the dimension with B. Well, that works if A and B are finite. If you want relative dimension over an infinite set, you could say that the dimension of A over C is the minimum of the dimension of A over the finite subsets of C. Okay, so once you've got that, you could then define the D-closure of a subset C to be those things in M whose dimension over C is 0. This is what you do in a vector space. Yeah? You have a notion of dimension for a subset, the closure of a subset is those things which have dimension 0 over the set. Okay, and you can define D-independence by saying that A is D-independent from C over B if the dimension of A over B together with C is the same as the dimension of A over B. Okay, so more axiomatics, I'm afraid, but perhaps more palatable ones. Now, the lemma is that it's very easy to check, well known. This is a finite reclosure operation on M, and this D-independence does at least satisfy the first 5 conditions of being a stationary independence relation. And if the remaining conditions were to hold, we'd say that this would be stationary. Yeah. Okay, so if we've got some structure which in a reasonably natural way carries a dimension, then we might have a chance of extracting something useful out of it in this context. Okay, I want to translate this condition of moving almost maximally into this context. So let me do that. This is the notion of basic orbits. Well, roughly, basic orbits will correspond to strongly minimal sets in Laskar's result. Yeah? And we'll want to just look at moving maximally on basic orbits. Moving almost maximally on basic orbits. Okay, so let's suppose we've got one of these dimension functions. Once again, script x is closures of finite subsets. And just a bit of notation here, if B is in M and C is one of these closures of a finite set, the orbit of B over C is what you expect it to be. It's all the places you can send B to using things from the pointwise stabilizer of C. Okay, so we will say that, so given B and A, one of these closed sets, we'll say that B is basic over A if B is not in A, and whenever C contains A and the dimension of B over C is less than the dimension of B over A, then B is actually in C. Yeah. So the dimension of B over A is as small as it can be without it being 0. Yeah. Okay, so obviously if the dimension of B over A is 1, then B is going to be basic over A because my dimension function is integer valued. Yeah. Okay, and just by sort of minimization, if B is not in A, then you can find some C containing A such that B is basic over C. And the nice thing about these, one of the nice things about this is that if D is such that all its elements are basic over, let's say, A, then D closure actually gives you a pre-geometry on D. Okay, so now we'll say that an automorphism H is bounded if there's some, okay, so this is, I'm saying bounded here, rather than moves almost maximally, so it's sort of the opposite. We'll say H is bounded if there's some closed set C and B which is basic over C, such that for all B prime in the orbit of B over C, H of B prime is in the closure of C B prime. So that's very much like what was happening in the vector space example, yeah? When we talked about bounded automorphism. Or, in that case, not moving almost maximally. Okay, so that's the definition. And Theorem B here is sort of what you get out of Theorem A in this context. So suppose you've got a dimension function D, and this corresponding notion of independence is stationary. And suppose that you've got some closed set A for which there's a basic GA orbit D such that the whole of M is the closure of A together with D. All right, so this corresponds to, in Laskar's theorem, to there being a strongly minimal set in which the whole model is the algebraic closure. Yeah. Okay, so suppose you've got an automorphism G, little g, which fixes all of the things which are in the closure of the empty set, and suppose it's not bounded, as on the previous slide. Then every element of G, this automorphisms which fix every element of the empty set, every element of G is a product of 96. We've gone up to 96 now. 96 conjugates of G plus or its inverse. Okay, so this is really like Laskar's theorem. It's a sort of abstracted version of Laskar's theorem. Rather than having a strongly minimal set, we've got this thing D. And rather than having algebraic closure, we've got a more general notion of closure. Okay, well, what's the proof? Well, this isn't the full proof, but these are the sort of steps. So you've got this, this automorphism little g. It's not necessarily stabilizing or fixing every element in this set A. So what you do is you take a commutator, let's call the resulting commutator G prime, which fixes every element of capital A and which still isn't bounded. Yeah? Then you prove that it moves almost maximally over A. And then you apply the Tenz-Ziegler theorem A. So that means that every element of the pointwise stabilizer of capital A is a product of 32 conjugates of G to the plus or minus 1. And then if you take, it's almost an exercise, it's in Laskar's paper, if you take something in G which moves A to something independent from itself over the empty set, then G can be written as a product of 3 copies of that pointwise stabilizer, and so you get 3 times 32, which is 96, which is the number in there. Yeah. Okay, so roughly those are the steps in the proof. It's just a matter of, I mean, the only thing you actually have to think about perhaps is the first one, this business of taking the commutator. So it really follows from Theorem A. Well, that's not what my theory. Yes, I mean, so there are examples of this setup where you have bounded automorphisms, and so if you wanted to show that something was simple, as well as using this theorem, you would also have to show that the only bounded automorphism is the identity. Yes. Yeah. Right. So we'll come to that. Yeah. Okay. So that's the theorem. Let me give you some applications of theorems A and B to the Hrushovski constructions. So let me remind you what these constructions are. Let's take a sort of reasonably rudimentary form of the construction. So let's fix some integers r, m, and n. The language we'll work with will just have an r-ary relation symbol, and script C will be the class of R uniform hypergraphs, so structures in which this relation is irreflexive and symmetric. So irreflexive and symmetric. So an instance of this relation in a structure in C is just a subset, a subset of size R. Okay, so if B is one of these R uniform hypergraphs, R square bracket C just consists of the hyperedges. Yeah? So the set of subsets which are related by R. Okay, so I want this as subsets really rather than tuples, just because we're now going to sort of count the elements in this set. So if we take one of these finite R uniform hypergraphs, we'll define the pre-dimension of B to be n times the number of vertices minus m times the number of hyperedges. Okay. Well, so then we want a sort of a notion of one hypergraph being nicely embedded in another in this context. So if B is a finite substructure of C, let's write B less than or equal to C, and let's just say B is strong in C, because it's quicker. I sometimes say B is self-sufficient in C. B is strong in C means that the pre-dimension of B is less than or equal to the pre-dimension of anything that contains B. Yeah? So the pre-dimension doesn't get smaller on overgraph. Okay, well, you can see that works if B is finite. You can adapt it to be meaningful if, in the case where the smallest structure might be infinite. So A is strong in C means A intersect X is strong in X for all finite substructures X of C. And of course, you have to prove that this actually means the same thing. So there's a lemma hidden behind that. Okay, so this is the notion. All of this is due to Hrushovski. This is the notion of a substructure being strong in the larger structure. It's a nice notion because it's transitive, for example. So if A is strong in B and B is strong in C, then A is strong in C. Well, it requires a proof. It's not completely obvious, but it's true. And then you take C0 to be those structures in which the empty set is strong. So what that means is that delta of B is greater than or equal to 0 for every finite B. Okay, so C0, in C0, the finite substructures are very sparse. Yeah? Because let's just look. So what does it mean for delta B to be greater than or equal to 0? That means that the number of relations on B is at most n over m times the number of points in B. Yeah? So they're quite sparse hypergraphs, but they're interesting nevertheless. Okay, one thing to observe is that if you take a finite subset X of some structure C in this class, then there's some Y, finite Y, above X, where delta of Y is as small as it possibly can be for sets that contain X. Yeah? Simply because I said that these m and n are integers. Okay, and all these delta Y are bounded below by 0. Okay, so once you've got a Y with that property, you can see that Y is going to be strong in C. Because if you take something bigger than it, it still contains X, and therefore it can't have delta values smaller than Y. Okay, so another nice thing about these structures is that you can amalgamate them. Okay, so at least over strong substructures. So if A is strong in B and C, and these structures B and C are in class C0, then the free amalgam F of B and C over A is again in the class, and B and C are going to be strong in F. Yeah? Okay, so given that, you can do a Hrushovski type construction and show that there's a countable structure, M0 in C0, unique up to isomorphism by a sort of usual back and forth argument with the following two properties. First of all, that if you take any finite hypergraph in C0, then this can be embedded as a strong substructure of M0. And secondly, you have this homogeneity property, too. If A1 and A2 are strong in M0 and are finite, and H is an isomorphism between them, then it extends to an automorphism. So it's just a classic Hrushovski construction. Now, I mean, this is an interesting structure for many reasons from a model theorist point of view. It's omega stable of infinite Morley range. But you know, it's a nice structure, even if you're not that keen on stability theory. Okay, so why does it have a dimension? Well, if X is a finite subset of M0, you can just let the dimension of X be the minimum of the pre-dimensions, this delta of y for y containing x. Yeah? So we just looked at that sort of thing a few minutes ago. Okay, so this really is a dimension function. And in general, if you take the closure of x, finite subset of x, with respect to this dimension function, so this is going to be those things in M0 where the dimension of x together with a is the same as the dimension of x. This is actually going to be infinite, and it properly contains the algebraic closure. So from a model theoretic point of view, this is different from algebraic closure. It's bigger than algebraic closure, which sort of makes it a bit more interesting. Makes it different. Okay, but you still have, so even though it's not algebraic closure, you still have homogeneity properties. So the first one says, suppose A1 and A2 are closures of finite sets, and H is an isomorphism between them, then it still extends to an automorphism of M0. Okay, so this is not the homogeneity that was on the previous slide. This is a sort of stronger thing. Yeah? This is extending automorphisms between closed sets in this sense. And the second thing is just saying this is stationary. Yeah? Declosure, this de-independence in this context is stationary. The second thing there is reasonably non-trivial to prove. The proof we have uses essentially the calculation in Hrushovski's proof of the algebraic amalgamation lemma, if you know what that is. So the hard amalgamation lemma in Hrushovski's paper. Okay, but there's something slightly mysterious about that. But the end result is that for this example, we've got a stationary independence relation compatible with the closure. So we can apply Theorem B there. I've just recalled what the definitions are. There are some sort of degenerate cases we have to exclude. So let's suppose that if we're looking at graphs, so r equals 2, then the n there is bigger than m. And otherwise, we'll assume that n is at least as big as m. Let G be the group of automorphisms which fix the closure of the empty set. Okay, so to apply the theorem, we need a basic orbit in which where the closure gives you the whole of the model, gives you the whole of M0, and the first part just says that any basic orbit will do. The second part says the only bounded automorphisms are trivial. Okay. And the third part is really just a matter of applying those first two parts, and you get this G is simple because if you take a non-trivial automorphism, then every element of G is a product of 96 conjugates of it or its inverse. Okay, so we get that for these Hrushovski constructions. But maybe you're not so interested in that example because it wasn't omega categorical or anything, and that's going too far away from what the meeting's about. So let me remind you of how you use this, what you do to this construction, or what Hrushovski does to this construction to get omega categorical structures. Okay, so the same setup as in the theorem on the previous slide, but now we've also got this function f, so it goes from non-negative reals to non-negative reals. It's continuous, increasing, tending to infinity as x tends to infinity. You consider Cf to be structures in C0 where delta of x is greater or equal to f of the number of points in x for all finite x in A. Yeah? So on the previous, so for C, you just have delta x greater or equal to 0. Now it's bounded below by this function of the size of x. Yeah? Okay. But we do the same thing. I haven't told you what sort of F you should have in mind at the moment, but we'll do that shortly. So just temporarily, if A is a subset of B and B is in this class CF, write closure of A in B, well, the same definition, it's those B and B such that the dimension of B over A is 0. And we'll write that A is declosed in B if this yes, no, I got it right. Yeah. If the closure of A is just A. Yeah. So that means that if you pass to a bigger set in B from A, then the dimension has to go up. Okay. Well, if you stare at this for long enough, what you find is that this closure is bounded. So closure of X in some structure in this class is bounded by a function of the size of X. Yeah? So there's a uniform bound in terms of the size of X on the size of these closures. We will say that a function is good if the finite structures in this class, together with this notion of being a strong substructure, has the free amalgamation property. So that means that if A is closed in B1 and B2, then the free amalgam of B1 and B2 over A should still be in the class. Well, that's not very exciting unless there are some good functions. And the condition that Hrushovski gives is that if you take a sort of something that doesn't grow too quickly, so something that grows sort of logarithmically, then you will get a free amalgamation class. Yeah. Okay, so once you've got a free amalgamation class, you can do a Hrushovski construction. So if F is good, then there's a countable structure MF unique up to isomorphism such that any structure in the class can be, any finite structure in the class can be embedded as a closed substructure of MF. And the homogeneity property, if A1 and A2 are declosed and finite, and H is an isomorphism between them, then it extends to an automorphism. And okay, so using this and the fact that the closure is uniformly bounded, you get that this structure is omega categorical. And the second bullet point there is just saying that if you play around with some of the initial values, you can get various transitivity conditions. So for example, if you take F0 to be 0, F1 equals n, then the closure of the empty set will be the empty set, and the automorphism group will be transitive. Okay. Well, it's not a stationary independence relation. No, I'm not going to explain why. It's very easy to see that this is not a stationary independence relation, I promise. So, you have to make it a bit stronger to get the stationarity. So, what we say is that, so our new independence relation, the one that we actually want to apply a theorem to, is this orthogonal symbol here. So, we'll write A is very independent from C over B, yeah? Meaning A is D-independent from C over B, so that's just like in the previous case, and the closure of A and B and C is the union of the closure of A and B together with the closure of B and C. So that's sort of as small as it possibly could be. It will turn out that from the first condition, this closure is the free amalgam of these things on the right-hand side over the closure of B. Okay, now this thing is a stationary independence relation compatible with the closure. And so we can apply Theorem A. Yeah? All right, so suppose F is good and we want the automorphism group to be transitive. Suppose we've got the following extra condition. If A is a basic orbit over B, then MF is in the closure of B together with E. Here's the result. Okay, we'll come back to that star thing. Take a non-identity automorphism and take A closed such that there's a basic GA orbit, then, well, what you do, these are the sort of the steps in the proof. You show that you can take a commutator of your given G, which fixes every element in A. Well, that's not terribly hard. Then what you show is that something non-trivial fixing every element of A, it moves almost maximally over A with respect to the one that's not a stationary independence relation. Yeah? Okay, but then by taking another commutator, that's what's happening in the third one, you get something which moves almost maximally with respect to the thing that is a stationary independence relation. Then you apply Theorem A. You do the arithmetic, you get 192 conjugates. Oh, and you also use Laskar's trick about writing the automorphism group as a product of three conjugates of the pointwise stabilizer of A. Yeah? And it comes out to 192, isn't that nice? But what about this extra condition? It's surprisingly difficult. So you're just being asked to show that everything lies in the closure of a basic orbit. Yeah? Well, we've done it in some special cases. We've done it in sort of my favorite two special cases. We've done it in the graph case, where the pre-dimension is given by twice the number of vertices minus the number of edges. And we've done it in the sort of hypergraph case with R at least 3, where the pre-dimension is number of vertices minus number of edges. So in these cases, the automorphism group is a simple group. And, well, I don't know quite why it's so difficult, but those are some problems, and I'm over time, so I'll stop. Yeah. Yes. Well, that's the sort of second question here. Yeah. Okay. Yeah. So if rather than working with integers m and n, I take some irrational alpha and take alpha times the number of vertices minus the number of edges. Yeah. Then then there's an M0, and it turns out that there's a 0-1 law associated to choosing hypergraphs where you choose the edges with probability n to the minus alpha, or maybe it's 1 over alpha in this case. Yeah? And the limit theory is exactly the limit theory of, it is exactly the theory of this M0. No, so that's yeah, so what happens if you, or you can do the Hrushovski omega categorical construction, the one that gives you stable omega categorical structures, where again you have a suitable irrational alpha. Somehow you don't have the dimension function to sort of tell you what a basic orbit should be, and it becomes a bit harder. Yeah. Yeah. So that's the second question. Yeah.
Is there any chance that in the very first original theorem about matter, the number 8 can be decreased, say, to 3? Or is there a counterexample?
I don't know, actually. I'm fairly sure that in some of the later ones, one could be a bit more careful about taking commutators lots of times. I'm not sure. I mean, you're the experts on this. Yeah, I mean, 8 seemed very good, actually, to me. 8 seemed really good. Yeah, no. Yeah.
3 might be.
Yeah. I would have been impressed with 16, actually. But
the 8 is in the
yeah, where it's not.
Yeah, I mean, in the bounded horizontal space, we can prove that the isometric group is a simple group, but it certainly will not be boundedly simple, because you have things that move just by a tiny, tiny bit, and so you need arbitrary measures like this in order to...
We don't have an omega categorical example.
Yeah, but he's not talking
Yeah.
about
No.
that. I was asking about, really the context of
Yeah.
because I think, all these theorems that were proved were always like this, that you can count the number of conjugates to me.
Yeah. Yes.
Yeah.
No, I don't know an example. Yeah.
All that.